to quickly go through for you just to explain, and then we're going to do our notes. And then after we've done our notes, the write up the prac and some notes about it, then you've got some exercises to do. Right, first things first. We established the motor effect that a wire with a current through it experiences the force of magnetic field. It's only, guys, while the current is flowing, and that's because when you've got a current through a wire, you've got a magnetic field around it. Okay, so if I represent a wire as a dot like that, that would represent a current coming out of the board. Okay? So a dot like that represents a current, or anything going, an X is going in. So if current's coming out of the board, you can work, the magnetic field around it, which I'll draw in red, is radial. It's just a series of rings like that. And they should be even. Which direction are they going though? For coming out of the board, what you do is get your right hand, the right hand grip rule, remember, thumb out. So the fingers wrap around anti-clockwise. So this field is an anti-clockwise field. Now, if the... There we go. That's what happens when you get too close to the board and you... Right, so a magnetic field, don't forget, is defined as the direction that a north pole will go. So it's from the north to the south. So if I put a north pole in here, it's going to travel around that wire. Okay? Now, if I have a wire with a current coming outwards, sorry, that's a current going into there. Yeah, you can draw it quickly.
So we've got the circle, then another circle, then another circle, but it's going this way.
Okay, now, just for clarification, they are obviously a similar current because the spacing in the field is very similar. If that was double the current, you'd have double the number of concentric rings there to represent it, right? Okay, so you have currents going through, you've got magnetic fields around the wire, you're going to have a force applied, right? Pretty obvious.
Yeah.
If you have them going in the same direction, and I'll just draw the wire with a little circle around it, you're going to have one field, which is going around this one like that, right? You know, and it's in that direction, correct? This field around that one, it's also going in that direction. Because we're in the same direction, they effectively add together. So what you end up with in green is you'll end up with that one close to the wire, that one close to the wire. This one will join with that field and you end up with that sort of shape, like Kermit the Frog. I don't know if this will work for this one. That's the shape of the field, right? What do you notice about the number of lines around the outside of the wire compared to the lines in the middle? So here's the wire now. I'll just draw as a dot. How many field lines are there outside the wires compared to the middle? There are a lot more on the outside than the middle. You've got what you could think of this as a field density or a field pressure, and so consequently it will push the wires inwards together. Okay? Now, in the other... that over there, because these things are only... I'm effectively making a straight short across those, and so they're drawing more than 5 amps, which just makes it go. Now, another way, I can actually do it like this. If I take this field and move it over that one, they're in opposite directions, aren't they?
Yeah, so they're repelled.
So what will happen is they can't cross over and they won't join together. So what happens effectively is this one's okay. This one, though, is going to get pushed in to accommodate it. That one has to get pushed inwards like that. Similarly, this one, that's okay. That one will get flattened round. That one will get flattened round. And so when you pull these two out, If I can get the green and the green, only lets me do one at a time, of course, it's not multi-touch board. If you look, you end up with double number of field lines in the middle compared to the outside ones, and so consequently you can predict that you're going to get a motion that way for the wire, which is repulsion.
That's a force.
It applies a force and accelerates it. Yep. No, you got 1, 2, 3. It's the field density which is counting here. No, they're not. They go both go in the same direction in the middle. That one's going that way. That one's going that way. Yes, they are. That one's going that way. That one's going that way. So they both go down the middle. That one's going. No, they're not. That one's for the current going out of the board there, coming out of the board and going into the board. What I've got, Brad, is got a wire here with the current coming out. Got a wire here with the current going in. I've got a magnetic field going that way around that one. Magnetic field going that way around that one. And they repel. And we saw that happening there. They repel each other, yeah. The other one was attracting it. When they were in the same direction, they were attracting.
In opposite directions, they repel.
Same direction, attract. It's in the book, you can review that.
In this case, attract, do not attract. Similar forces repel, but in this case, similar forces attract.
It's not similar forces, it's the direction of the current. It's just because you've got current in the same direction, the field adds, and it ends up with a greater field density on the outside. It adds and goes. I know what you're saying, but it's just different. Now, don't go off magnets, go off what happens. Okay, very quickly. I've got to go through three more things relatively quickly with you to explain work, and then I'm going to give you the textbook to go over it with. First thing, motor effect. What things do you need for there to be a motor effect? You need a current.
Magnetic field.
You need a magnetic field. And you see what?
Force.
You see the force, and there's something else that is important in it. You have some length of conductor. Don't you? I mean, I is the current, B is the magnetic field, L is the length of the conductor. So obviously there's a relationship here, and the relationship is F equals the strength of the field times the current times the length of the conductor inside the field. And the answer is, funnily enough, there are some rules that go with this. The first one is the direction of the forces acting. Okay? So
What is B for again?
that's the magnetic field, measured in Teslas, and we'll do some notes on this. I is the current measured in amps, L is the length, right, of the wire inside the field. So, if I have a magnetic field, I'll explain that in a second. If I have a uniform magnetic field, which isn't being drawn very uniformly there, B, upwards, and it's a metre across it, and I have a current carrying conductor with the current I going that way across the board, being the direction that a positive charge would flow in the line, right, in the wire. Which way will the force be in this thing? So you've got 90, at the moment you've got 90 degrees between the wire and the magnetic field. Which way will this experience a force? Now, for physics I don't explain to you, they actually work at 90 degrees to each other, and we use the FBI hand rule. Now, the way I was taught this, and it's easy enough to remember, is that the FBI carry guns. So you've got a gun with a trigger, right? And of course the FBI represent the directions that things occur. So my thumb...
And your index finger, you put it up, makes an L.
What? Yeah, it is, FBI. So that F is my middle finger, which is force. B, which is my pointer finger, is the magnetic field. I, which is my thumb, which is the current. And so to work out the direction of the force in this case, B will be up the board, I will be from left to right, So this wire is experiencing a force straight out of the board.
So the wire is the black line.
The wire is the black line.
So and electricity's going that way. So
The current is going that way, not...
the red line's going around the thing like that.
No, this is just a magnetic field going straight up and down. So I have a magnet sitting down here. There's a magnet just sitting there. Like the other day on top of the scar, we had a magnet sitting there with this magnetic field.
Yeah.
I just have a wire running over the top of it, with a current going through it, and it will experience a force, in this case, either left or right. Yes, in fact, in this case, and it has to do with some physics, the three objects, the current, the magnetic field, and the force experienced all act at right angles to each other.
So you've got a magnet.
Which is why we have to take this into account sometimes.
So I'm saying, if you have the magnet like that, why wouldn't it go like that?
If I've got a magnet where?
You've got a magnet there, and the wire wouldn't go there.
So if the magnetic field, in this case, was left to right with the wire, so change the question. So you've got a magnetic field going this way across the board, right?
So magnet.
And then you have a wire in there with a current going that way. Magnet will be sitting...
The magnet doesn't go up. A magnet's attracted.
It's just a magnet sitting on a wall or something. It's just a stationary magnet.
Yeah, but why is it repelling?
It's not repelling, that's just the magnetic field lines.
Oh,
That's where the magnetic field goes, is in red.
yeah.
Okay? So from that magnet, that's the north end of the magnet, right? So there's a field coming out from it.
So if you look at
To make this a uniform field, what you'd need is another magnet up here with a south on that side.
if you look at this on 3D, you'll see the magnet like that and the field going like that.
No.
About the FBI, which way is the force going? You said once
All right,
something's coming out.
let's go slowly. I'll do another one for you, Jack, to show. And you'll have a lot of questions to do on this anyway, so that's not a problem. You'll get to practice it. Let's do it like this. I have magnet there, north end, magnet here, south end, right, on this face. So this is the south, that's the north. I'm going to get a uniform field between these two plane magnets like that, aren't I?
Yeah.
So the field goes left to right. Everyone can see that? That's simple?
Excluding the fact that the field also go out like that.
I'm ignoring the little bow at the end and all that, but between a north and a south like that, it will be a uniform magnetic field between it. So then I have a wire. Let's put the wire at 90 degrees running through there. The wire has some current, and I'll make the current run downwards in this case. So now to work out the direction of the force, I look at F, B and I, my middle finger being F, which is what I want to work out. B is the magnetic field, which is going from left to right. I is down, which means the force is out of the board. So that wire is experiencing a force pushing it outwards from the board. You see, that's what happens. You see people in tests, they're sitting there going, like this, trying to get it to work. It has to be right hand. So if you're left-handed, forget
If the force, like, if those red lines going opposite way, then it would be going
into the board. Exactly.
So F is the middle finger, right?
Yep. F, B, I.
So if we so because the current is going down, we twist our thumb upside down, and then F is coming out of the page, the magnetic thing is going sideways.
Going cross like that. Yep.
So you actually see people in the test just pull up.
I do.
Yeah, no, I got it.
When you're supervising tests and you get to the magnetic field question, you see people go like this. It's really strange. Okay. The reason for the sign here. Okay. Let's so I can tell the time. So I had a uniform magnetic field going into the page. And I have a wire, and let's put a distance on this. Let's make that distance 1 metre. Okay. Let's make that 2 metres. I have a wire. Now, first of all, I have a current. Let's do it this time. From there to there,
Going to the right.
and it's going downwards, right?
Current's going to the right.
And current is going down the board.
I mean, the
So let's do this again. B into the board. I is downwards, which twist my hand over, which means, as you say, the force in the Y is towards the right.
What? I thought you said that the force was.
Look, F, B, I. So B into the board. I is down. F is across the board.
Oh, so that's a new example.
That's a new example. Now, in this case, if I then had a second wire, which was also 1 metre long, and was going across there, which way is this wire experiencing force? The force for this wire is at 90 degrees, is like that. What can you tell me about the size of that force compared to the size of that force on this one? It's what? It's the same. It is the same. Now,
So the force. So if you had that in real life.
be careful. I'm explaining something that is a bit of a trap for people here. If I was to draw, if you think about this piece of paper, right? As being the plane that the magnetic field's coming at, right? So the magnetic field is actually going into the board at 90 degrees like this. That's right. So there's a magnetic field going this way. What angle is the wire to, first of all, what angle is the wire here to the magnetic field? Yes, you can see. There's the magnetic field going in, there's the wire. What angle is it? It's 90 degrees. What angle is that black wire, the second wire, to the magnetic field here? 90 degrees. It doesn't matter how I orientate it on that plane, it's still at 90 degrees, isn't it?
It is.
Well, it becomes relevant when you have this situation. What happens? What happens here
Yeah, tell me the direction of the current.
is the force only applies to the part of the current which is at 90 degrees to the magnetic field. So I've got a current travelling up here, right? At some angle. Now remember about vectors, the part of this wire, well, the part of the current which is experiencing the force is the part of it that's at 90 degrees to the field. So that's where the sine theta comes in. It's to make a sort of take into account that it's only the force only experienced as a part of the field.
That one was F.
Oh, this one I just did.
No, in the hair. So you got that one F, that one B, and that one I.
Yep,
What's B again?
magnetic field strength. You can also just do it like this. You can have your hand flat if you like, and it's F, B, I. That's okay too. So it's the palm, the point of the fingers, and the thumb. You can do that as F, B, and I. But I was just taught gun because it was popular in my day. There was a show called FBI, and they all had guns. So that's how it went. Second thing I'm going to quickly do before we do notes and then give you questions. It will be. I think they are. So let's do a quick example here. Now, a 5 Tesla field is very strong. If I don't give you a direction, what do you assume? It's at 90 degrees. You just assume you don't need the sine theta. So, as always, you're going to put your data in. Calculate force is what you want. This is a plug and chug question. You just put B equals, what did I say, 5 Tesla. That's enough to knock your fillings out. I equals 2 amps. And L equals 4 meters.
So Tesla is the strength either measure what?
The strength of the magnetic field. Tesla's is magnetic field strength. And I'll put that in your notes. A is amps for current, and of course length is in meters. So we just do the old F equals. Now you always put your formula in. Then you substitute in, putting your units.
What's that with L?
It's just a symbol for length. 5 times 2 is 10 times 4 is 40. So that's a 40 Newton force on the wire. I mean, you guys can handle that. Straight, simple maths. It's just in newtons. Force is always newtons. Unless you go to America and they use strange units. Foot pounds.
Foot pounds.
For every foot there's a pound of force.
Foot pounds.
There's America. Just,
Did they already want you guys to do that?
Yeah, like in Australia, you've got everything which are units which you can relate to each other, whereas if you're in America and you're trying to calculate like something, you can't. Like just everything's just... So, what units are you using, Jimmy? Oh, ice cream to go to Mexico.
yeah. Have you guys got that?
Ice cream to go to Mexico?
Yeah.
Oh, I haven't got ice cream to Mexico.
What is this message?
Could you do me a favour, Marnie, just throw the light on so I can actually see and read, because my eyes are not up to... Thank you. Right, and the other thing we've seen, I won't use that. Yeah, when you're using this formula, just be really careful to work out the angle between the current and the magnetic field. Don't just assume because they put an angle on the page that you need to use it. It's an old HSC trick where they put a magnetic field like this, right? And then they put a line like that and put 45 in, number 45 in there, and ask you to calculate it, and yet that is still at 90 degrees, so the sine theta doesn't count, and the number of students get caught out by that. Well, the field's like that, right? So the angle between the wire and the field is 90 degrees. So the sine just becomes 1.
How would you know it's not
When does the sign help?
Well, if in this case, if when you have it, where it does count, would be the case where you have a field like I had. I should have used my technology, shouldn't I? I forgot I could do this. Could have just moved the wire out. Okay, there's my uniform magnetic field.
Just imagine something.
Actually, I can't do it that way. I have to do it somewhat. Sorry, that's my mistake. I should have done like this. If my magnetic field is like this, there's a magnetic field that way, and if my wire runs like that across it, and that's 45 in there, then I have to use sine 45. Because they are not, that wire is not at 90 degrees to the field.
So it's a sign 45, which is...
Yeah. Yeah. Okay, other thing quickly. We also, of course, there will be a formula that goes with 2 wires running parallel to each other. Now, if I have 2 wires where the currents go in the same direction, they will attract. If there's the same length with the same current in both, there will be a certain force acting. If I then reverse the direction of the current in one, they'll repel. What sort of force will they have compared to the other way? They'll be opposite directions, but it will be the same size, same magnitude, because it's the same current, same distance separating and all that. Now there is, of course, a formula which we have to know to be able to do that. And of course, the things that influence it is the current in the two wires. The only direction influences in or out, not the direction of the field. Doesn't affect the size. The length of them, of course, is important. Is there anything else that's going to be important about it? No, not just the length. Distance between them. Yep.
How much stuff can we do on electricity circuit?
In terms of motors, and this is just intro to how motors work, because obviously magnets and current is what make motors work.
Okay.
So this is just really intro stuff to that. And the formula is F per unit length of wire equals the magnetic constant times the current over the distance. Now, the magnetic constant, K, is 2 times 10 to the minus, better check it, 7 things. You don't need to know the units of that.
What are the units for that?
Oh, I knew you'd ask that.
Is there going to be a way
I don't know.
M per meter squared pi?
It's going to be, if you work it out, it's going to be newtons per metre. No, the metres cancel out, so that's good. That's gone. It's going to be newtons per amp squared. Okay, let's do a really, really quick example. So e.g. you have 3 metres of wire, and I'm just going to write it quick. There's a current running through wire 1 of 2 amps, current running through wire 2 of 3 amps. They have a space between them of 50 centimetres. Find the force per unit length. So you're going to have F on 3 equals 2 times 10 to the minus 7 times 2 times 3 all over. What do I put underneath? Marnie, what do I put underneath? It's 50 centimetres distance? Pardon? I wouldn't. What do you have to convert into? 0.5. So you get that, you put it in your calculator, which I don't think I have a calculator on my board, do I? Wish I did have. Did I put a calculator in here? Put it online, did I?
So K like the gravitational constant.
It's just a constant that makes things work.
Relative to each question or just this?
If you see a K in that formula, you use that number. Yep. So I'm just putting my calculator at the moment, times 2 times 3 equals, divide by 0.5 equals, and then I have to multiply that by 3 to get the force, and I engineer that. You can see now why I needed to put a lot of amps through that to get a force that was big enough to be able to actually accelerate the wires apart. That's in centimetres, so it has to be 0.5 of a metre. Yep.
You actually, like, you know how you get a short because like the wires start to heat up. you could actually say cool it with something like liquid nitrogen.
You can keep doing it. Better still, you can make superconductors which don't heat up. Force is 7.2 times 10 to the minus 6 newtons per metre.
So that's it.
Oh, I should put newtons per metre there, shouldn't I?
But I mean, that's
Yeah, what I did is I got that multiplied by 3 to find newtons per metre. Yep.
I don't know much about motors at all, but
Good.
a car engine works. Doesn't it like combustion makes pistons go up and down and that drives the wheels? But how is that electromagnetic?
It's not.
But I thought you said that that's how motors work.
We're doing electric motors. One's Prius, yes, they're the ones which use this stuff. If you have an electric motor, it uses electricity. If a combustion motor, it uses petrol or diesel. They have gas.
Yeah, that's really petrol or diesel, not both.
Yeah, don't put both in the same tank. It don't work.